Shivang Thakkar, registration number 298.
Rahul Singla, registration 299.
Rishav Goswami, registration number 303.
Topic is system model in deadlock.
So let me start with introduction to deadlock. What is a deadlock? Simply put, a deadlock occurs when a set of processes are blocked because each holds a resource and waits for another resource held by one of the other blocked processes. Consider an example. Process P1 holds resource R1 and waits for R2, while P2 holds R2 and waits for R1. So they are forever stuck. Now I would like to talk about system model. System model defines how these processes and resources interact. The model includes processes P1, P2, resource R1, R2, and specific resource instances, which we assume a fixed number of resource instances are available. Now I would like to talk about RAG, also known as Resource Allocation Graph. We model these instructions using Resource Allocation Graph or RAG. This graph has two types of edges: a request edge from a process to resource, and assignment edge from a resource to a process. The key takeaway from RAG is if a cycle appears in the graph, it indicates a potential deadlock where processes wait indefinitely for each other's resources. Now here you can see in the graph that an RAG is defined by resource is a rectangle and assignment edge is present as well as, and detection deadlock can be seen from the flowchart. Now I would like to talk about the four necessary conditions of deadlock, also known as Coffman conditions, which are as follows: mutual exclusion, hold and wait, no preemption, and circular wait. This is the flowchart for the same, where we can see that R1 holds to process 1, which is also can be taken by resource 2, but it is indefinitely waiting because process 1 has never left the resource 1, while process 2 is also using R2, so a deadlock condition can be created. Here is an example scenario. P1 holds resource R1 and requests R2. P2 holds resource R2 and requests R1. So the observation we can see is each process is waiting for a resource held by the other. Neither process can proceed. So the result is it forms a circular chain of waiting condition. All processes in the cycle are held together and blocked in a deadlock condition. And here is the same for an visualized by bar graph, where we can see the time periods of process 1, process 2, and process 3.
Ensuring at least one of the necessary conditions of Coffman never happens. In avoidance, allocates resources carefully at runtime to keep the system in a safe state, preventing deadlocks before they occur. And in detection, it leads deadlocks, but check the system periodically to find them. And in recovery, after detection, resolves deadlocks by terminating processes or preempting resources to break the cycle. This is a deadlock handling overview of the flowchart. Here, it also tells about the safe state and unsafe state. In this, it basically tells that if the program before execution, that if the program is in safe state, then it will execute. But if it's in an unsafe state, it will wait and the process keeps going on. Deadlock prevention ensures one of the Kaufman conditions is broken, and the Kaufman conditions are no preemption, hold and wait, mutual exclusion, and no preemption. This is the deadlock prevention flowchart. Here, the process 1 is waiting for resource 1, but it is assigned with resource 2. And for process 1, it is assigned with resource 1, but it is waiting for resource 2. Now, the process 1 has to wait for resource 2 before it executes. Same for process 2, it has to wait for resource 1 before it executes. But it will not work because it is in a deadlock, because either the process 1 or the process 2 has to leave their resources before they can gain the other resource. Deadlock avoidance. It is basically implemented in Banker's algorithm. It first checks the request if the need is smaller than available. If the need is greater than available, then it will straight away go to the unsafe state and the process will be on wait and it will not execute. Whereas if the need is smaller than available, then it will be in a safe state and it grants the request to execute the program and the further request will be applied, and it also checks the safety check all processes which will be finished in a safe sequence. This is a basic flowchart which explains the algorithm of bankers. It first checks request if it is smaller than need or smaller than available. Then it pretends to allocate it, and if it is in safe state, then it will execute, and if it's not in safe state, it will wait. Now, this is an example of banker's algorithm. Here, there are basically three main steps to do this. First is we have to take out the need matrix, and to take out the need matrix, we have to do max minus allocation. After we do max minus allocation, we'll create one more column which will be of need matrix, and then we have to go for the second step. The second step is we have to ensure that the need matrix is always smaller than available. After that is ensured, and the need matrix is smaller than available, then it will execute. And if it's not smaller, then it will not execute. And in the third step is to that if the need is smaller than available, then we have to do the further calculation, which is actually that after the execution, we have to plus the allocation with the available.
Okay. Deadlock detection. When deadlocks aren't avoided, the system detects them by checking the resource allocation graph. If a cycle exists, some processes are deadlocked. In this flowchart, we see that we look for cycles. If a cycle is detected, it's a deadlock. And if there is no cycle, it's a safe system. So now to recover from a deadlock, after detection, we recover it by either terminating or preempting resources. So for that, we have two methods, process termination and resource preemption. In process termination, we enter one or more deadlock processes to free resources. But in resource preemption, we temporarily take the resources from some processes and reassign them to other processes to break the deadlock cycle. Here, in this flow chart, we see that we detect, choose a victim, abort or preempt, and resume the other processes. This way, we can restore normal execution very quickly. In this graph, we see how system's safety status is shown. And now take a look at real life examples. In databases, two transactions may hold each other's logs, whereas in OS, threads can wait forever for devices, which is a classic deadlock example. Now, let's look at the summary. Deadlock is equal to the processes stuck waiting for each other. We handle it through prevention, avoidance, detection, and recovery. In the summary flowchart, we see that we have identify, prevent or avoid, detect, and recover. This way, we can see the full life cycle of deadlock handling. And now, these are the references we used for our presentation. Thank you.